We have another example problem here. We have a figure that has 3 charges. They're all on the corners of a rectangle. So since there's only 3 charges, there's a corner that does not have a charge. So our problem says the charge in the bottom right corner of the figure is labeled as Q. That is equal to negative 10 nanocoulombs. What are the magnitude and direction of the electric field at the bottom left corner of the rectangle? So this hiding space over here, there is no charge located there. But each of these 3 other charges are creating their own electric fields, and they are all contributing to the overall electric field at that point. So I'm going to number them, 1, 2, and 3. We need to determine the electric field of all of them individually and then add them up. So E1. So charge 1 is this top left positive charge. We know that positive charges create electric fields that point away from them. So I want to represent that at the dot where I'm trying to find the overall electric field. We'll find the numerical value in a minute. Charge 2 over here, this negative 5 nanocoulomb charge, it's farther away. We will need to determine how far we're asking for the field from that charge at that point. Because this charge is negative, the electric field that it creates will point towards it. So I need to draw a vector representing that. It points directly along the line connecting the 2 charges. And it points towards that charge because it is a negative charge. Charge 3 is also negative, so it will be creating an electric field that points towards it as well. I should draw E1 longer because it's going to be bigger, both because the charge is bigger, but also it's closer. So I'll just draw that longer. So we were trying to find the magnitude and direction of this overall electric field, meaning we need to add together all 3 of these electric fields, figure out what the electric field is at that location, and then magnitude and direction means just the strength of the electric field overall, and direction means what angle does it point at. Okay, so our equation, the electric field created by a point charge. Our constant, the charge we're talking about, how far from the charge, so that distance squared. And then our hat is the unit vector describing this radial direction. So E1, we have to write all of these in terms of their x and y components because to add vectors, we can only add x components to x components, y components to y components. So we need all 3 of these in terms of x and y. So K is this constant, 8.99 times 10 to the 9. The charge, E1, is the 15 nanocoulombs. I do need to put the nano, 10 to the negative 9. The distance between the 15 nanocoulomb charge and the point we're trying to find the field at is 1 centimeter, which I do want that in meters, again, for my units to come out and be newtons per coulomb. Sorry. So this is the magnitude R hat is the direction. We know that E1 points straight down. So I'm going to go ahead and just put the negative J hat there because we know it points only in one direction. Let me plug these numbers in. I'm keeping a few digits since I'm not at a final answer. This is a big number. We have 10 to the positive 6. With the electric forces, we have really small numbers. But because our electric field doesn't involve two charges, these numbers do tend to be quite large. Okay, so E1, negative y direction, we have its magnitude as well. Let's look at E3 next, simply because it's all in the positive x direction, and that just makes it easier. So I'm just using this same equation again, but plugging in the values of the charge. Oh, that was the wrong charge, sorry. E3 is the one from the 10 nanocoulomb charge. And I'm just putting in the magnitude because I'm going to account for the direction separately. So this distance between Q and the point where we're trying to find the overall field is that 3 centimeters, which needs to be in meters. And I know the direction already is positive I hat. This is another situation where you want to be very careful to make sure your overall vector you come up with is making sense in the coordinate system. So this one I'm getting 9.9888 forever. So 10 to the 4th. Newtons per coulomb. And that's in the positive I hat direction. Now, the reason I mentioned make sure you make sense, if you put the negative value of Q in and then positive I hat, you would have come up with a negative answer, which now would mean to the left, which is not correct. So we just need to follow through on those signs. The positive and minus has to do with the direction specifically. All right, E2, the electric field. Now we will need that distance r between the charge itself and the point we're trying to find the electric field. We can use Pythagorean theorem to do that. (3.1623) centimeters. We will need to convert it to meters when we're plugging it into the equation. All right, so the magnitude, we're going to have the 8.99 times 10 to the 9. The charge is 5 nanocoulombs. The distance, 0.031623 squared. This is the magnitude. It's going to have both x and y components though, right? We look at it over here in our picture, it points to the right and upwards. If I was to redraw it just so we can picture it, we have this x component to the right and this y component pointing upwards. So to find the x component, I would need the magnitude and multiply it by the cosine of whatever this angle is that it makes with the horizontal axis. The y component would be the magnitude times the sine of that same angle. So we essentially can say that E2, the vector itself, is E2 cosine theta in the x direction, so I hat, plus E2 sine theta in the y direction, j hat. The way I have it written right now, we've already found the magnitude of E2. So I'm going to finish this off by putting in cosine of theta, I hat, plus sine of theta, j hat, because I already have E. I can go ahead and calculate that if I want to. The magnitude is 4.4949 times 10 to the 4th newtons per coulomb. So now we're just going to end up multiplying by cosine theta and sine theta. So we need to figure out theta. This angle, I'm going to come over to the left here, tangent of theta is the opposite side. So I'm actually going to use the dimensions of the original rectangle to find this. The opposite side has a height of 1 centimeter. The adjacent side has a height of 3 centimeters. Take the inverse tangent of 1/3, I get 18.435 degrees. That's what I need to come over here and put in for my angle. Oh, can't lose my unit vectors, I hat and j hat. Okay. Going to move upwards a little bit. And I want to keep my E1 and E3 in my screen. So I'm going to erase just this bottom part, so I have a little more room to write. So E2, our vector E2, I'm going to go ahead and factor those through so I have my overall x component and y component. So 4.2643 times 10 to the 4th. I'm just trying to keep the same number of decimal places. Plus electric field times the sine of this angle, 1.4214 times 10 to the 4th j hat. Okay, so again, we're trying to find the overall electric field, which means I need to add these vectors together. I can add x components to x components to get my overall x component. So the 9.9889 exponent 4 plus what we just got, the 4.2643 exponent 4. These add to 1.4253 times 10 to the 5. And that is now our x component of the overall electric field vector. Which hopefully makes sense. If we come back to the picture, not the number itself, but that we should have a bigger x component because they were both in the positive x direction. Now we add y components to y components. This, even just looking back at my original picture, I expect this to point downwards. And that's because E1 is bigger, so a larger value overall. So plugging these x values in and adding them, I'm getting negative 1.3343 times 10 to the 6th j hat. And again, the negative sign is for the direction. So this would be the electric field in terms of its components, in terms of vector notation. The problem, though, wanted us to find the magnitude and direction of this electric field. So we need to find overall how strong this electric field is and in what direction it points. I always draw these components out to make sure I'm making sense of where my angle is located. So I have an x component that points to the right, because we have a positive value, and then I have a y component that points down. I'm representing the down with the arrow and just putting the magnitude on the side. So what we have right now is this 90 degrees. We have the x component and y component of this overall vector. We want this total overall magnitude, meaning how long is this vector I've just drawn? This new vector I've drawn represents the overall electric field at that point. So the magnitude is the length of that vector, and then we need direction as an angle. The magnitude we can get from Pythagorean theorem. We have the x component, we have the y component. So by plugging these in, we can get the magnitude. And we typically, instead of writing the absolute value signs around the vector, we typically just write the E without the vector sign. So I'm plugging these numbers in. I'm going to round now. I can't remember how many sig figs we had, maybe 2. So 1.3 times 10 to the 6th. Our units are newtons per coulomb. You could put in meganewtons instead of the 10 to the 6th if you'd want. So there's our magnitude. The direction is our angle. And I'm going to solve specifically for the angle I already labeled in my picture. I know the tangent of that angle is the opposite side, which would be this y component, over the adjacent side, which is this x component. So when I take the inverse tangent of that, I'm getting 84 degrees. Now, I just put their magnitudes in. I didn't put a negative number for the EY because I know my calculator doesn't distinguish between the first and third quadrants and the second and fourth. So this is why I always draw my triangle and make sure that I personally am reasoning through this direction. I do know this angle is downwards below the positive x-axis. So I can say the magnitude is this 1.3 times 10 to the 6 newtons per coulomb, and put negative 84 degrees as the direction. That's perfect. The angle is always measured like the polar coordinate angle, so measured from the positive x-axis.